Let's look at number 20 on page 194. The question is to find the extreme values of the function and where they occur for the equation y equals x cubed minus 2x plus 4. No interval is given to us, so we have to assume that it's on the interval of the entire domain of the function, all values that work in the function. Well, there's no number that we can't plug in for x for this equation and get a real number out. So our interval is from negative infinity to positive infinity. It's all real numbers. So now before we dive into the calculus of this, we ought to take a second to think about what the fact that it's a cubic function means for us. We're familiar enough with cubic graphs to know what they look like. They look something like this, or maybe that. And we've seen a few that have had the humps sort of stretched out so that they lose their up and down hump, and it can look something like that. These are all rough sketches. That thing should be continuing to go over to the left here, more like that. But as you look at these graphs, if we're interested in the domain from all real numbers, negative infinity to positive infinity, it's pretty easy to see there's not going to be an absolute minimum and an absolute maximum. Because however we draw it, whether we draw it like this one on the left or this one in the middle, it goes down forever on one end, and it goes up forever on one end. So we're definitely not going to have an absolute max and an absolute min. But we might have local maxes and mins if we have these humps in the middle. Maybe there are no humps. So our goal here is not to look for absolute maxes and mins, but instead to look for local maxes and mins, see if there are any, and decide where they might be. Okay. So we're looking for extreme values. Well, candidates for extreme values are found at the end points of the interval and at critical points, points where the derivative equals 0 or the derivative doesn't exist. End points of the interval, there are no end points of the interval. We're going for all real numbers, so we don't have to worry about end points of the interval here. This part is taken care of for us. I'm going to cross it out. Whoa, didn't mean to do that though. I'm going to cross that part out. But we are interested in where the derivative equals 0 or the derivative doesn't exist, and let's look at those. So the derivative is a pretty easy one for us to figure out. It's 3x squared minus 2. 3x squared minus 2, what values of x make that thing not exist? There aren't any. We can put in any number for x, and the derivative exists. So it exists for all x. When does it equal 0? Well, if you set that equal to 0 and solve for x, it won't take you very long to figure out that x has to be the positive or negative square root of 2/3, which, if we turn that into a decimal, is about 0.816, positive or negative. Alright, so we make our table of candidates when x equals positive square root of 2/3 or negative square root of 2/3, and we just plug those values into the original function for y. I've got that labeled g of x because I pulled that over from question number 12. That should be y right here. Get rid of that. This is y. Okay. And we can see that y takes on the values of 2.911 when it's the square root of 2/3 and 5.087 when it's negative square root of 2/3. So those are our only candidates for extreme values. We can take this and go on to the next level and say, well, now I know that it's got a local minimum value of 2.911 at square root of 2/3 and a local maximum value of 5.087 at negative square root of 2/3. How do we know that one's a min and one's a max? That's really a topic for us to think about more later, but we'll touch on it real quickly here. We knew it was a cubic function, so it was going to look like either that, doggone it, I wonder how I can get rid of that. We knew it was either going to look like this or like this if we have local mins and maxes. And now look at this. The high one is to the left. It's at negative square root of 2/3. The low one is to the right. It's at positive square root of 2/3. So we need the low one on the right and the high one on the left. That's this. It's got to be this. And so we can see that the one on the left, that's got to be a local max. So it's negative. The one on the right has to be a local min, just from knowing the shape of the graph. We'll worry about how to do it when we don't know the shape of the graph coming up pretty soon, but not today.